Hi everyone. Today we're going to be talking about the Earth's interior, specifically the layers of the Earth. So let's get started. So the Earth is made up of many layers, specifically the outermost part, which is the crust, the mantle, core, and inner core. We're going to get more deep into it as we go in the video. But first, please take out your Earth Science Reference Table, page 10. On that page, you should be able to see an outline of the Earth's interior, its pressure, the pressure of each layer, and the temperature of each layer. You should also have your note packet out. Once you have it out, please write down our first note of the day. The Earth's interior has many layers, and you can find these layers on the ESRT, Earth Science Reference Table, page 10. Pause the video if you need to write this down. So the outermost layer, which is all the way out over here, is what we're standing on right now, and it's called the crust. There are two types of crust, the continental crust right here and the oceanic crust. The continental crust can be found on the land that we're standing on, and the oceanic crust is found underneath the oceans. So, just like I said, the two types of crust are the oceanic crust and the continental crust, which can also be found on this area of your reference table. And this is what the crust is, the very outermost layer. So, the continental crust is a lot thicker than the oceanic crust, as you can see here. The continental crust is about 5 to 25 miles thick, whereas the oceanic crust is about 3 to 5 miles thick. And you can see it in this image as well. The continental crust is a lot thicker than the oceanic crust right here. So let's write that down. Pause the video if you need to. Our oceanic crust is thinner, and the continental crust is thicker. So you can also see or find the density of the continental and the oceanic crust on your reference table, as you can see here. And we can see that the continental crust has a density of 2.7 grams per cubic centimeters, and the oceanic crust has a density of 3 grams per cubic centimeters. So this means that the oceanic crust is more dense than the continental crust. You don't have to memorize this, it's on your reference table. Let's write that down. Our oceanic crust is thinner but more dense, and our continental crust is thicker but less dense. Pause the video if you need to. So, our reference table also tells us what the different types of crust are made up of. So our continental crust is actually made granitic or made up of granite. So remember the igneous rock chart we have on our reference table? You can see granite is an igneous rock. It's lighter in color. So our continental crust is actually lighter in color. Our continental crust is lower in density, and it's also felsic, meaning it's very rich in silica, Si, or aluminum, and aluminum, Al. So this is what our continental crust is made up of, and these are our characteristics of the continental crust because it's granitic or made up of granite. Our oceanic crust is made up of another type of igneous rock, mostly basalt, and you can see basalt is actually darker. So our oceanic crust is darker, it is higher in density, and it's mafic, meaning it's richer in iron, Fe, and magnesium, Mg. So this is a summary of what I just talked about. Our continental crust is thicker. It's more felsic, meaning lighter in color, less dense, and rich in silica and aluminum. And it's mostly made up of granite. Our oceanic crust is thinner, it's mafic, it's higher in density, and mostly made up of basalt. So we're done with the crust over here. Underneath that is what we call the moho line. This line right here, it's called the moho. The moho is just the boundary between the crust up here that we're standing on and the mantle below it. So what we call the crust and the upper part of the mantle right here is called the lithosphere. So the lithosphere from here to here is the crust and the upper part of the mantle that is solid. You can also see it right here. This is our crust. The white part is the upper part of the mantle. Rigid mantle means solid mantle, so this part is solid. And both of these together is what we call the lithosphere. And the lithosphere is actually the top of part of it, the crust is what we're standing on. And it's actually broken up into plates or smaller pieces called plates, as you can see here. So this is the world map. And you can see the different smaller plates that the crust or the lithosphere is broken into. Let's talk about what's underneath that. So we talked about the two different types of crust, the continental, the oceanic. Our lithosphere is made up of the crust and the upper part of the mantle, which is solid. But right underneath the solid part of the mantle is what we call the asthenosphere. This part of the mantle is not solid and not liquid either. It's kind of gooey in texture. We call this texture plastic. It's somewhere in between solid and liquid. And you can find that right underneath the lithosphere, as you can see here. So, quick vocabulary words, and it's optional for you to write this down in your notebook as well. Rigid, as you can see here, the rigid mantle is solid. Rigid means solid. And plastic means it's the texture is in between a solid and a liquid, kind of like a gooey, slimy almost texture. And this is what our plastic mantle is. The asthenosphere is plastic. It's in between a solid and a liquid. But right above that, the part of the mantle that's part of the lithosphere is rigid, it's solid. So here's the thing. We said that the asthenosphere right here is plastic. It's in between a solid and a liquid. And we know that inside the earth is really hot. So that heat inside the earth will cause this plastic mantle in between a solid and liquid to create convection currents, as you can see here. So the heat of the earth comes from the inner part of the earth called the inner core. And that heat causes these convection currents to form in the asthenosphere because it's in between a solid and a liquid. This is also where we find our magma in the asthenosphere. So, what happens is, since the asthenosphere is going through these convection currents from the heat, sometimes as the asthenosphere is moving, it will cause the plates in the lithosphere above it to move with it. And what happens sometimes is the plates of the lithosphere, the pieces of the lithosphere, will start to move away from each other because of the convection currents within the asthenosphere, as you can see here. This gap that is formed in the middle when the plates of the lithosphere move apart is called a mid-ocean ridge. And this gap invites magma to come towards the surface of the earth, which can cause volcanoes to form and earthquakes to form. So what a mid-ocean ridge is, it is a continuous series of volcanoes underwater that form because the lithosphere is moving or the plates of the lithosphere are moving apart from each other because there are convection currents happening underneath it in the asthenosphere. And you can actually see an example of this in your reference table as well. This is called the Mid-Atlantic Ridge. A Mid-Atlantic Ridge is an example of a mid-ocean ridge, just like we saw here. And it happens right here in the Atlantic Ocean, as you can see. And you can see the series of volcanoes. We said a mid-ocean ridge is a series of volcanoes underwater. And this forms because the plates of the lithosphere are moving apart from each other, causing these volcanoes to form when the magma rises, and it's all because of the convection currents in the asthenosphere. What also happens is we know that there are convection currents in the asthenosphere. So sometimes in parts of the asthenosphere, the magma is moving towards itself, as you can see here. This will cause the plates, the lithosphere plates on top, to move towards each other as well. Now, in the past, we said that the oceanic crust is more dense and the continental crust is less dense. So if an oceanic crust meets a continental crust when they're moving towards each other because of the asthenosphere, the oceanic crust will sink because it is more dense. So as you can see here, the continental crust will move towards the oceanic crust or vice versa, and you can see that here as well. When they meet, since the oceanic crust is more dense or higher in density, it will start to sink underneath the continental crust, as you can see here. And so once it does that, since it comes in contact with the magma now, it will start to melt and form volcanoes and rise, as you can see here. Let's write that down. Pause this video and write this down. So the oceanic crust is more dense, so it will sink if it meets the continental crust. The continental crust is less dense, so it will float if it meets the oceanic crust. And this can start to, the sinking of the oceanic crust can start to melt it, and that will cause the magma to rise and form a volcano. Notice that there's something called a trench in this image as well. What is a trench? So, a trench is a long, narrow dip or depression in the Earth's crust, and it's usually deeper than the land around it. And it forms when this oceanic crust subducts or moves underneath the continental crust because it's more dense. You can actually see an example of this in your reference table as well, and you can see a trench can be found in the Pacific Ocean. The trench found in the Pacific Ocean is actually the deepest known trench in the world, and it's called the Mariana Trench, and you can see that right here and right here. The very bottom part of the Mariana Trench is called the Challenger Deep. And as you can see, once the oceanic crust has moved underneath the continental crust, it forms this narrow, very long dip. And this is what we call a trench. It's the deepest part of the world. So the Mariana Trench, as you can see, is found in the western Pacific Ocean. Now let's move on to underneath the asthenosphere. So underneath the asthenosphere, our mantle gets stiff again. It becomes solid, more solid. So as you can see, we have the crust, as we've spoken about. The asthenosphere is semi-liquid, semi-solid. This is where our convection currents form. And then we have a stiffer mantle right here. It's a little more solid. Let's move on to the outer core. The outer core and the inner core are our innermost parts of the earth, and as you can see, they're both made up of iron and nickel. Iron and nickel. So, what's the difference? The difference is that the outer core is actually liquid. This part right here is actually liquid, and the very inner core is solid. So we can also find the densities of each layer on your reference table right here. So we already know the density of the continental crust is 2.7, the density of the oceanic crust is 3.0. You can see the stiffer mantle has a density of 3.4 to 5.6, outer core has a density of 9.9 to 12.2, and so on. You can also notice that as you go deeper into the earth, our density is actually increasing, meaning the inner core is more higher density than the outer core, which is higher in density than the stiffer mantle, and so on. Now, if you go even further down in your chart, it shows you the pressure of each layer. So if I asked you, what is the pressure of the boundary between the stiffer mantle and the outer core? You can follow the highlighted area that is shown over here. And as you can see, if I go down here and I stop at this line that is given to me, and I go more towards the left on my y scale or y-axis, I can see my pressure is around 1.5 million atmospheres for the boundary between the stiffer mantle and the outer core. If I asked you the pressure of the boundary between the outer core and the inner core, you would just follow that line down once again. You would stop at this black line, go towards the left, towards the y axis. The pressure between the inner core and the outer core, or that boundary, is about 3 million atmospheres. You can also find the temperature. So if I asked you the temperature of the boundary between the stiffer mantle and the outer core, you would just go down all the way to the temperature the chart, stop at the black line that's given to you already, that's plotted for you, go towards the left. Now, our temperature of the boundary between the stiffer mantle and the outer core is around 5,000 degrees Celsius. Now, how do I know which layer is solid and which layer is liquid? This is also shown in your reference table right here. You just have to notice what the melting point and the interior temperature is. So the interior temperature line, this line right here, shows you the actual temperature of the layer, and the melting point shows you the point or the temperature at which that layer will melt or become a liquid. So let's look at the stiffer mantle right here. If I go down, I see the stiffer mantle's interior temperature, its actual temperature, is a lot lower than its melting point, the temperature that it will melt at. So that means my temperature of the stiffer mantle did not reach its melting point yet. It did not melt yet. So that's why it's solid. If I look at the outer core, you can see its temperature, its interior temperature is higher than the melting point, meaning the temperature has already passed the point at which it will melt. So that's why it's a liquid, because its interior temperature is higher than the melting point, the point that it will melt. It already passed the melting point. Now, the inner core, you can see the melting point is actually higher than the interior temperature, or the interior temperature of the inner core is actually still much lower than the melting point, which means it did not melt yet. That's why our inner core is solid. So if my interior temperature is higher than my melting point, as you can see, if my temperature passes or is higher than my melting point, then that layer is a liquid. Our outer core is a liquid. Finally, the very bottom of our chart shows how deep each layer is. So if I ask you what is the depth or how deep is the boundary between the stiffer mantle and the outer core, you'll just go from the boundary all the way down to the depth, and I can see the depth of that boundary is 3,000 kilometers deep. And that's about it for today. Thank you so much. Have a good one.